Hello and welcome to the Data Engineering Podcast, the show about modern data management. Have you ever woken up to a crisis because a number on a dashboard is broken and no one knows why, or sent out frustrating Slack messages trying to find the right dataset, or tried to understand what a column name means? Our friends at Atlan started out as a data team themselves and faced all this collaboration chaos. They started building Atlan as an internal tool for themselves. Atlan is a collaborative workspace for data-driven teams, like GitHub for engineering or Figma for design teams. By acting as a virtual hub for data assets ranging from tables and dashboards to SQL snippets and code, Atlan enables teams to create a single source of truth for all of their data assets, and collaborate across the modern data stack through deep integrations with tools like Snowflake, Slack, Looker, and more. Go to dataengineeringpodcast.com/Atlan today, that's ATLAN, and sign up for a free trial. If you're a Data Engineering Podcast listener, you get credits worth $3,000 on an annual subscription. When you're ready to build your next pipeline and want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With their managed Kubernetes platform, it's now even easier to deploy and scale your workflows, or try out the latest Helm charts from tools like Pulsar, Pachyderm, and Dagster. With simple pricing, fast networking, object storage, and worldwide data centers, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode today, that's LINODE, and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Your host is Tobias Macy, and today I'm interviewing Kevin Kho about Fugue, a library that offers a unified interface for distributed computing that lets users execute Python, Pandas, and SQL code on Spark and Dask without rewrites. So, Kevin, can you start by introducing yourself?
My name is Kevin, and I work for Prefect as an open source community engineer. Prefect is a workflow orchestration company, and my day job is helping our users adopt workflow orchestration. So I primarily help them through Slack and GitHub. And then on the side, I maintain Fugue, which we'll be discussing today.
And do you remember how you first got involved in the area of data?
Yeah, so I was a data scientist for 4 years before joining Prefect. And I think it's just natural that as a data scientist, the more technical data scientists get pushed further and further back into the stack. So at my last job, we were full stack data scientists and responsible for the data engineering of the pipelines that we needed in order to perform our data science work. And just in general, as we went deeper into the data warehouse, we had to use Spark more because of the volume of data that we were ingesting. So while I was at that job, I watched the Spark AI and Data Summit, and then there I met Han, who was presenting about Fugue at that time. And then that's when I started, working on open source, getting involved in Fugue, which we'll discuss later. And then I ended up joining Prefect because somebody that I presented Fugue to, told me, hey, you're probably a good fit for this role at Prefect. So I ended up talking to them. I wasn't, looking to change job, but then I found that Prefect was a place where I could grow, learn to grow my own open source project. So it's kind of interesting that, my day job is open source workflow orchestration. And my side hustle in Fugue, or this Fugue project, is all about open source, a compute focused framework.
Given the fact that Fugue is targeted to abstract across these different execution engines to allow people to go from single machine to distributed systems, I'm wondering if you can talk to some of the core goals behind the project and maybe some of the story, as much as you're aware of anyway, about how it came to be and what it was that was lacking in the ecosystem that made this a worthwhile endeavor.
Yeah, so there was this previous guest on this podcast from Bodo.ai. His name was Esan, their CTO. He framed this problem really well, right? He talked about this performance productivity gap with high performance computing. And he was talking about that in order to optimize the performance of programs with your high performance computing cluster, you really have to go deep, into C++ or deep into these compilers to be able to optimize performance. And in the same way, we find that in distributed compute, there's the same problem where if you want to get your code as performant as possible, it takes a significant amount of effort, specialized effort, in order to optimize every little bit. And we felt that this was a barrier to adopting distributed compute. A lot of times, if like new to distributed compute, it's very easy to just, try Spark out, write some code, and then, put that into production. But if you're not familiar with a lot of the concepts that are required to fine tune your program, it's very easy to fall into these pitfalls of having inefficient execution, right? So Fugue is meant to bridge that gap from, local execution and bring your code without any rewrites to distributed execution. The core goals of Fugue are basically that nobody should need to have specialized knowledge in order to harness distributed compute. We want to minimize the effort for big data projects. And when we talk about effort, we talk about execution, development, and maintenance of these big data projects, because you can have really good performing code, but if it's at the expense of, very long development and very high maintenance, then it's not worth it. Whereas you can have, code that's not performing as great, but at the same time, you can churn a lot of products out faster. So Fugue is meant to minimize the total effort across all these three things: execution, development, and maintenance. So our goal is to provide guardrails around your code so that when you bring it to a distributed setting, at a baseline level, it should perform above average compared to if an experienced, Spark developer was writing that code. And we do this by enforcing best practices. Like, for example, we enforce schema. Because like with Dask, for example, if you don't provide schema, there's a risk of rerunning, code twice to infer that schema. So it easily doubles the computation that can be easily avoided if you just provided the schema beforehand. Second is that there's a lot of boilerplate code when it comes to distributed compute. A lot of times, like if you want to bring like a Pandas function over to Spark, you often have to write maybe 2 or 3 helper functions just to bring it over. And at that point, you introduce a lot of boilerplate code into your code base, and it becomes harder to just focus on the logic. And along with adding all of this boilerplate code, you're writing more code that you then have to unit test, right? So aside from my original function, I now have to write tests for those 2 to 3 helper functions that are bringing that code over to Spark. And because there's such a high effort to maintain a good code base, we find that people end up not following best practices and trying to just, get code out in production, because it's very hard to adhere to best practices when you have so much boilerplate code. So with Fugue, we believe that the code should adapt to the user. You already have your logic defined, and we want to be responsible for bringing that to Spark for you. We believe that the code should adapt to the user, because currently with Pandas and Spark and any compute framework in general, we find that your logic and the execution of that is coupled together. So if you write your code in Pandas, it describes both the logic and the execution. Same thing with Spark. You normally have, your transformations alongside your partitioning strategy and how it's going to execute distributedly. We want to simplify this by decoupling logic and execution. So can I define my code in native Python or in Pandas or even in SQL, and then worry about the execution later? And then we find there's a lot of benefits when you're able to decouple it this way.
As far as the target users for Fugue, I'm wondering if you can talk to the different personas that you either envision as you're designing some of the features or working through the implementation details, or actual concrete examples of the types of role that are using Fugue in your experience of working with the community, and some of the ways that those users and personas influence the way that you think about the feature priorities and the design of the APIs and interfaces, and what the kind of core capabilities and core foundational principles of the framework actually are.
Yeah, so before I talk about like who the target user is, I think it's helpful to describe what the journey is for an average person that starts their distributed compute journey. So, for example, with a small to medium sized company in a small data science team, I write all my code in Pandas, and I have these pipelines already in production. But then now the data is starting to get too big for Pandas to properly handle. For those who are not as familiar, Pandas is single core. There's no like multi-processing, and it's also confined to one machine, right? So when the data becomes too big for a single machine, that's when you have to scale out to a distributed framework like Spark or Dask that can take advantage of a cluster and distribute that data over several machines that work on it in parallel. So for that data scientist, with a relatively small company without a lot of resources, the very tempting thing to do is just to increase to scale vertically, meaning that I have a machine that has maybe 16 gig of RAM. I'm running out of RAM. I'll just bump it up to 32 gigs, and then I'll keep running that same pipeline. But of course, this isn't efficient, right? Because a lot of times, maybe you only need 20 gigs of RAM for a single step, and then otherwise the utilization is low all throughout, right? So scaling vertically tends to be very expensive. It's not a good use of resources compared to if I could scale horizontally, where I could introduce more machines and I can divide my data across several machines. Now I can have auto scaling enabled, which Spark and Dask provide, and I can have my cluster scale up for only the steps that need a lot of resources, and then I can scale down when I don't need as much resources. So now we have this data scientist who's in a dilemma. Hey, do I scale vertically where I can just bump up the resources, or do I scale horizontally, but that would involve rewriting my code in a way that makes it distributable, right? So now I have Pandas based code base, and now I have to convert that to either Spark or Dask. So on the Fugue side, we want to make this transition seamless, but for the very basic use case, maybe you just have one step that's very intensive that you want to parallelize. And that's why Fugue opened the transform function. And the transform function takes your Python code as is and then brings it to the distributed execution for just one function. But then if you want like a full workflow, then Fugue also has an API for that. So if we treat your program as a set of logical steps, Fugue creates a DAG out of this logic. And if you treat it as just logic without execution, then we have this execution agnostic DAG, right? So we just have a set of logical steps that's not necessarily coupled to Spark or coupled to Pandas, right? And at this lower level, because you committed more of your code into Fugue, Fugue provides other benefits. For example, we can do some compile time checking to see if the schema is accurate throughout that DAG and see if there's some downstream operation that will not have a column that it needs. In that situation, we can raise a compile time error, preventing expensive mistakes using your production clusters. And then even if you're experienced with Spark or Dask already, there's still a lot of edge cases that are hard to develop for. For example, if I have 10 items that I want to distribute over to a cluster, and each of these 10 items takes 1 hour to process, what you'll find is that, hey, I'm going to divide these 10 items, send them to the workers. You'll find that it's very common that one of those workers or one of those partitions has 2 items and another one will have 0. And this is just because of the default hashing that happens. Although, to be fair, at larger scales with more partitions, it kind of gets averaged out and you kind of have even partitions. But there are cases when, for example, want to train 10 machine learning models. Now what happens is that partition that ends up having 2, items to train can easily double the total execution time of your program. So this is something that we solved on the Fugue level that allows you to just specify, hey, I want even partitioning, and we guarantee that on our end. Something that's also used a lot that takes a lot of effort to code on your own is checkpointing. So in Spark, what happens is if your lineage gets too long, where you have a lot of steps in your program, you eventually run into errors because this lineage is too long. So the best practice around it is to truncate your lineage by explicitly checkpointing and then fetching out that file later and loading it back in. So on the Fugue level, we have added more checkpoints. For example, do you need this to be a permanent checkpoint or just a temporary checkpoint to break the lineage? We also added, for example, this concept of a deterministic checkpoint. So if you're in a Jupyter notebook and you're just iterating, now we can load that checkpoint in if the code that produced that checkpoint remained the same. But if something changed there, then our determinism is lost. So that's when we decide to rerun the code and generate a new data frame, right? So even for experienced Spark users, there's a lot of cases where you have to write a non-trivial amount of code in order to get things to work as efficiently as possible. So Fugue provides a lot of that also for these already experienced Spark users. And what we find is that the average Spark user actually doesn't use Spark as effectively as possible. Again, like it's very easy to just put code out there, it's running, okay, but with some certain tweaks, it could be run much, much faster. So from our metrics, what we've seen is that in general, people that use Fugue, their costs have dropped 50%, and wall time of Spark jobs also drops by like 80%, right? And this is already, coming from a big company that has a lot of technical people. So we think that for the average Spark user, they'll probably see a lot of gains moving their code to Fugue because Fugue puts those guardrails and the best practices around it to execute it effectively. The second part of your question is how does this influence priorities and API design? So one of the things that we encountered was that we first introduced Fugue as the DAG, and this did not have that one-liner transform function. So now it was an all or nothing thing that I have to totally buy in to this DAG, to Fugue's DAG in order to get all of the benefits. What we found was that it was too constraining. People didn't really, like that. They just wanted something, hey, bring this function to Spark, bring this to Dask. And because of that, we exposed those like very high level APIs of just like one-liners in order to bring, one Pandas function over to Spark or one Pandas function over to Dask. The second thing to mention is that we also have a lot of people who they don't have a cluster. And because they don't have a cluster, there's really nothing to distribute to. Like you can't, use Spark or use Dask because you don't know how to obtain your own cluster. That's why on our end, on Fugue, we've been putting a lot of recent development into optimizing the local experience. For example, we added DuckDB as a backend. DuckDB is a in-memory OLAP database that now allows you to like query a CSV or a Parquet file, perform some SQL query on it, and get back like process results already, that which is now smaller, and then now you can process in Pandas.
Yeah, DuckDB is definitely an interesting project that I've been keeping an eye on. And my understanding is that it's effectively SQLite for analytical use cases and column-oriented aggregations.
Exactly, yeah. So for us, because we have a SQL interface as well, right? So where we were inspired by Spark SQL, and we have a SQL interface for both Dask and Pandas. But what we're finding is that the SQL interface that we have for Pandas, which is something that we wrote ourselves by mapping SQL commands over to Pandas code, is much slower than DuckDB. And I'm talking by like a magnitude of like 100 times, just because DuckDB is a very optimized for that like local querying of like Pandas data frames or querying from a file. And that's why we introduced it as a backend. So now you can use that on top of your Pandas data frames.
Every data project starts with collecting the information that will provide answers to your questions or inputs to your models. The web is the largest trove of information on the planet, and Oxylabs helps you unlock its potential. With the Oxylabs Scraper APIs, you can extract data from even JavaScript-heavy websites. Combined with their residential proxies, you can be sure that you'll have reliable and high-quality data whenever you need it. Go to dataengineeringpodcast.com/Oxylabs today and use code DEP25 to get your special discount on residential proxies. You've talked a little bit about some of the sharp edges or pitfalls that engineers run into when they're trying to move from a local development single machine environment to executing across a Spark or a Dask cluster. I'm wondering if there are any other sort of general categories of problems or points of confusion that people run into when they are trying to make that transition. And at the point where they do decide that I need to move this off of my laptop onto a cluster, how they think about what the decision points are for whether they want to use Spark or Dask in the event that they don't already have the existing infrastructure.
First off, a lot of people, when they see Fugue, they think that, oh, it's just some kind of mapper that, hey, I have some abstraction layer and I just decide if it's going to go to the Pandas code path or the Spark code path, and underneath the hood, like it just maps it, right? But what they don't realize is that a lot of Fugue is all about maintaining the consistency that you get the same results across these execution engines. Because Spark and Pandas, they generate a lot of different results for a lot of similar operations. For example, nulls join with nulls, or are nulls dropped from the join, right? In Pandas, they actually join together, while in Spark they don't. Same thing with group by. Are nulls kept in a group by operation, or are they dropped in the group by operation? So for this one specifically, for Spark, nulls are kept in the group by, and in Pandas, nulls are dropped from the group by, right? But this keeping or dropping of nulls, it's still understandable. You just have to write a bit of extra code. But the one that really stands out to me is sorting. Because in sorting, in Pandas, they decide, hey, are nulls at the bottom or are nulls at the top of the sort, right? Whereas in Spark, which is Java based, it treats nulls as the biggest value. So if you're descending, nulls are at the top. If you're ascending, nulls are at the bottom. So for sorting, we actually have two completely different systems for both Pandas and Spark. And now it becomes Fugue's question, or any framework that does some sort of like migrating Pandas code to Spark. It becomes a question of which one do you want to be consistent with. And on the Fugue side, we chose to be consistent with SQL and Spark, because if the code executes well on a distributed environment, then it can go backward to the local setting, whereas it's not necessarily true the other way around. So consistency is a big issue. And then the other one is also mindset related. A lot of people expect some functionality to exist in a distributed setting, and they may not be aware of how expensive that is, right? So for example, median is the most basic example, where a median in local in Pandas is trivial to execute. But if you bring the median operation to Spark or Dask and you're looking for a global median, it becomes way harder, because now data is spread across multiple machines and you need some kind of movement between that data in order to be able to get a median value, right? So same thing with transpose, right? Transpose is a very common operation in Pandas, but it's something that doesn't translate well to a distributed setting. So if you look at Koalas, for example, which aims to be a Pandas interface for Spark, I think in their documentation, they explicitly say that, hey, there is a limit of like, this doesn't perform well after 10,000, columns or 10,000 rows, right? So mindset is also definitely a big deal. And then aside from that, there's just a bunch of concepts that people are not exposed to on the local setting, but they have to be cognizant of in the distributed setting. So these are stuff like lazy evaluation, persisting, managing your partitions and the shuffling of data around, which can easily cause bottlenecks if you don't do things effectively, right? And then the second part of your question is, when would somebody choose Spark versus Dask? So on the Fugue level, because we're an abstraction layer for these two, we hope that our users don't really have to make this choice. I'm going to choose Spark or I'm going to choose Dask. Instead, it should be about, hey, my company already has a Spark cluster, so I'm just going to use that. Or, hey, my company already adopts Dask and uses a Dask cluster, so I'm just going to use that. But we can still answer this, question as fairly as possible, given that by doing the Fugue project, we interact a lot with Spark and Dask. So in general, it feels like Spark as a framework is more optimized. Because it's more mature, the optimizer is really developed. Whereas in Dask, I think we're still just about to start getting that optimizer into the data frames. The second thing is that, Fugue is all about data frames and being an abstraction for data frames. But you may have, certain use cases that don't fit into the data frame setting necessarily. And Dask has other structures that deal with this well. For example, you have the Dask bag, which is like the JSON kind of dictionary that you can deal with, or it has, the Dask array, which builds on top of the NumPy array, which is like a distributed array, right? So there are these other data structures, and like Dask also, you can do stuff like, and Prefect does this, where you can just submit tasks like, hey, run this function somewhere in the cluster, right? Spark doesn't have as much freedom for this. Spark is more constrained to that data frame, and because of that, more optimized and more performant in that data frame setting. If you don't have any cluster yet, though, like in your workplace, it's significantly easier in my opinion at least, to spin up a Dask cluster. Because of the Dask ecosystem, I can just spin up one on AWS Fargate, or I can spin one up on Kubernetes. But deploying Spark on Kubernetes myself, that's not something like I would even personally consider. It's quite challenging. So if you don't have anything, Dask is much easier to get a cluster for and scale your code. And then the last piece of comparing Spark and Dask is local execution, right? So because Spark runs on Java, you need to instantiate that Java environment. There's a lot of overhead to doing it. And it's kind of painful actually, because even if I'm developing locally and I'm running a script and I tweak my script and I try to run it again, it easily takes 20, 30 seconds to spin up that Java environment. Whereas in Dask, because it's all Python based and it builds on top of the Pandas and NumPy and the PyData stack, it's a lot more seamless to just easily test code and it just runs automatically.
In terms of kind of not necessarily prior art, but similar art in this ecosystem, the thing that comes most readily to mind is Modin. And you also mentioned Koalas, which is the Pandas API on top of Spark. But Modin is a little bit more in line with what Fugue is working on, where it provides different execution across either Dask or Ray. It also has some different interfaces beyond just the Pandas API, where it has a SQL layer. And I'm wondering if you can give your thoughts on the comparison between the goals and utility of Modin as it compares to what you're building with Fugue.
Yeah, definitely. So this is a question we get a lot just because people think, oh, porting Python Pandas code to Spark or Dask, you must be like Modin or you must be like Koalas, right? They put us in the same bucket. But actually, I don't think we are. So for Modin specifically, we've been looking to add Modin as a backend. So for those who are unfamiliar, Modin is a Pandas interface, but with a Dask backend. They have OmniSci as a backend, and I think they have Ray as a backend now, right? So on the Fugue level, we don't have Ray yet as an execution engine. And if Modin perfected that path of having an interface for Ray, we could easily add Modin as a backend to Fugue, right? So I think we're still one level of abstraction above from Modin where we could use them as a backend if it made sense to. But in general, Modin and Koalas are Pandas interfaces for distributed compute. And Fugue intentionally decides to not be a Pandas based interface. And then this becomes sort of a philosophical discussion now of, is a Pandas interface translatable to distributed compute? And we think it's not. And there's a couple of reasons for this. Number one, especially when we're talking about Spark, we brought up consistency earlier. So if I asked you, hey, is Koalas consistent with Pandas or is it consistent with Spark? Would you know the answer readily? And the thing is, not really, right? Because how am I going to use Koalas, right? A lot of their use cases, for example, involve having a Koalas data frame, and then maybe I'll convert it to Spark, and then maybe I'll run it through Spark ML or something, right? Or maybe I need to convert it to Spark in order to be able to use Spark SQL on it because I can't readily use Spark SQL on Koalas. But then if you read the documentation, Koalas is actually consistent with Pandas, right, in terms of how it handles nulls. And because of this discrepancy, it's a bit awkward in the middle, kind of not quite Pandas, but not quite Spark. I personally think that the design decisions become really hard. Like when you're working on a framework, if you want to be more oriented with Pandas or with Spark, especially if you're like a Pandas interface for distributed compute. The second thing about the Pandas interface is that in general, when you use Pandas, it's very tied to the index. You do a lot of operations that set index, reset index, you group by, it makes a new index, right? And if you're working with Pandas, the index is very, very ingrained in what you do. So Modin, when Modin created their project and when they were making their API, they decided to prioritize based on the order of how often the functions were used in Pandas, and then they would knock those out so that they could, get the most used functions in first. Index operations are in the top 5 of that. And that just shows how tied things are to the index. So why does Pandas have an index and why does Spark not have an index? And the answer is because the index is sort of a global ordering of all of your data. And in a local setting, that's very fine. That's no problem at all. In fact, it's very efficient for some operations because now I can easily say, hey, get me the item at index 20 or get me the item at this datetime index, and it's just fetched easily. But now if I have my data across multiple machines, maintaining a global order for that, especially as I do group by operations, it's certainly doable. It's very expensive, and it's very questionable if it's even needed. And that's why we think Spark chose not to have an index, because if I needed, so and so item at index 20, in Spark it would just translate to a filter operation where I can say, hey, get me the item that fulfills this criteria. And this is also why we think that with Koala specifically, there are a lot of cases where it's like, yes, it's a Pandas interface to Spark, but there's a lot of cases where performance doesn't really hit the bar that you'd expect, right? There's a lot of cases where, and you'll see this on Stack Overflow, where people perform a group by apply operation, and all of a sudden it's even running slower than native Pandas. And we think it has to do with that distributed index where you're maintaining that global order. So definitely the index is questionable, and we chose intentionally to not use the Pandas interface because it didn't necessarily translate well. The second thing with the Pandas interface is if a user just sticks to Pandas, they're not exposed to things like checkpointing, persisting, in distributed computers also broadcast. Pandas just doesn't have the grammar to necessarily apply these operations. And then the question becomes, hey, do I add these operations into the Pandas grammar, right? But if you do that, it kind of isn't necessarily a Pandas interface anymore, right? And it kind of deviates from it. There's a lot of times when Pandas has something that doesn't make sense, and you have to make a choice. Hey, do I deviate away from this operation? And then at that point, you kind of lose parity, right? The other thing I want to discuss is that it seems to be a bit magical in a lot of cases where a lot of times these frameworks will just say, hey, you just need to change the import statement and it's all going to distribute magically. This statement assumes that there is like a one-to-one parity between the Pandas interface and that framework's interface. And of course, like it's never going to have 100% parity because Pandas is developing, Pandas is changing, and then they're always going to be one step ahead. So now there's a question: if there's no API parity, like how does it fail on the distributed side? And I can tell you for Modin specifically, what their design decision was is that if something fails, it defaults back to Pandas. And what does defaulting back to Pandas means? It means collecting everything back into a Pandas data frame, performing that operation, and then spitting it back out, right, as a distributed data frame. And if you think about that, that's such an expensive way to do things that is a result of not really respecting the fact that I can bring this to Spark or Dask with these certain considerations. And we think at Fugue that if you just devote a bit more time and re-architect your solution in a different way, you'll be able to get much better performance and be very mindful of the distributed system components that you're interacting with, like partitioning and checkpointing.
As far as being able to abstract across some of those distributed systems concepts and kind of hide away some of that complexity and be able to do push down operations to optimize across the specific contexts of those execution engines, I'm wondering if you can talk to the implementation details of the Fugue project and some of the ways that you've thought about the architecture to allow for optimizing in these different execution engines and still being able to provide a consistent interface to the end user as they're developing and being able to maybe have some progressive reveal of complexity where at the top level it's just just pass it through this transform function, we'll do everything for you, or if there's something very bespoke or custom that you need to do, or being able to have some sort of pass-through capability to say, I want to be able to call into this utility of Spark ML to be able to build this model in this broader DAG, being able to actually maintain that capability but have that mapping back up to the Fugue API.
Yeah. This is a very loaded question, but I'll try my best to answer. So, on the first level with Fugue's architecture, again, like it's pretty much what you'd expect in some ways, where like, hey, if I naively made some kind of abstraction layer that, hey, when this join is called, go to the pandas join. If we're using a Spark backend, just use the Spark join, right? And I've talked to a lot of like engineers who kind of made their own solution to this, and they made their own abstraction layer. But then what they get bitten by is the consistencies that we mentioned earlier. So for Fugue, our guarantee is consistency, and we write that extra code so that you get the same results across different execution engines, right? So that's the first level. So first is for each of those operations, we go down to, pandas, or we go down to Spark or Dask, but we do it in a way that it's consistent across all of those engines. So this means that we have an execution engine spec that we've come up with. And this execution engine is kind of like the contract for what we need to be able to fulfill in order to add an execution engine. So, for example, if Ray came in, if we made an execution engine for Ray, we would need to be able to perform all of these operations, like how do I partition? How do I run a function inside a partition? How do I join, merge, etc.? And this is like the contract for what has to be fulfilled. Now, once we have this execution engine contract and we're true to it, now we can add engines and evaluate, hey, can they actually fulfill the spec of the execution engine? So from the unit testing perspective, we have a unified test suite for all of our execution engines, and we strongly maintain our 100% test coverage. And that's a very important thing for us because it takes a lot of effort to do so. But besides the abstraction, if Fugue is guaranteeing consistency, that is something that we have to uphold. So we have that unified testing suite, extensive unified testing suite that guarantees that. Now, once we have this execution engine, the second component of Fugue is that DAG, right? Or you can just bring one function to Spark or to Dask, but really what Fugue has is the abstraction layer has that full workflow as well, where you can bring all of your logic into the DAG, and then the DAG brings that to the underlying execution engine. So for example, if my logic were something like, hey, load this, perform some transformation, load this from another place, join them, and spit a file out, that is a logical graph that I can then say, hey, run this on Pandas, run this on Spark, or run this on Dask. So we have our own data frame that's engine agnostic. And this data frame, you perform operations on it. And as you perform operations on it, it's compiling that DAG, similar to Spark or Dask, right? Because when you have Spark operations and Dask operations, they're evaluated lazily. So we have our own like data frame that's evaluated lazily. And once that computation graph is created, you say, hey, run that graph on Dask. Then we go down to the Dask execution engine, and step by step we say, oh, let's use the Dask load, the Dask transform, the Dask join, and the Dask save, right? Same thing with Spark. If that execution engine went to Spark, you say, oh, use the Spark load, use the Spark transform, join, and then save. So it's the same thing. We have both of these for your standard operations, but then now we have to also provide stuff around execution. How do I partition? How do I broadcast? How do I checkpoint? The distributed computing operations that I talked about earlier. Now we add them also as operations with our distributed engine agnostic data frame. So these are the components that make Fugue. And then after that, it's all about adding the cherry on top of how can we make it even easier for people to use. So for example, we have this DAG now, we do schema validation, we raise errors if ever you're doing operations on columns that don't exist at a certain point. Or for example, when I said take in both native Python code and Pandas code, we can also operate independent of the Pandas framework, where we have functions that are defined on lists of dictionaries or lists of lists. We can also take in these data frame types, and we can also operate on them. So now you can describe your logic in whatever grammar you want, and then we can worry about bringing that to Spark or Dask for you. So now that we have these two components, we have a Python interface in that DAG. We can build the SQL layer on top of it, right? So we have a SQL interface in Fugue SQL. And the SQL interface is a first-class interface that shares all of the features of that Python interface. So in order to match that Python interface, we added keywords to SQL. So for example, you can use SQL to say load this and then do some transform using this Python function, join, and you can do that all in SQL. So when we designed Fugue SQL, it was meant to be a full end-to-end interface for compute workflows built on top of that abstraction layer with one-to-one parity.
As far as the execution engines, you mentioned some of the differences between Dask and Spark and some of the ways that you might optimize the execution across them for those specific contexts. And I'm curious, what would be involved in being able to expand to other execution engines where maybe you decide that we care more about being able to perform streaming compute, and so we want to be able to execute on top of Flink, or we want to, move from a data frame to a concrete table implementation, and so we want to be able to push down some of this logic into, Snowflake or Presto and an actual, database or query engine, and just some of the ways that you think about what are the extensions that make sense to invest in, and what are the points where we say that is out of scope for what we're trying to do with Fugue, and so we're not actually going to try and go after that target.
The things you mentioned are definitely things that we want to add in the future. Number one, streaming, and number two, like going deeper into the database. So for example, we can use the same like SQL interface query. Like when we said we want Fugue SQL to be an end-to-end interface, we can envision it querying from the database, loading it in some data frame, whether that be Pandas or Spark, and then doing your operations in Pandas and Spark that can't be done with ANSI SQL. So for that, we've been thinking about it. But the thing is, if we want to have a unified interface for everything, like for us, like we want to be able to run on Pandas, Spark, and Dask without, changing the underlying functions or changing the underlying code. We just want to specify the execution engine. The thing with databases is they have their own like custom functions. Like they have different ways to express the same thing, right? And because they have different ways to express the same thing, there is some design that needs to happen around mapping to make sure that, hey, if you use this Fugue SQL keyword or something, it will map to this function in MySQL or this function in Postgres or this function in Oracle, because they all have different ways, especially like around datetime stuff like that. So that's certainly been in our head. But on a more like realistic, like short-term level, for example, something that's really nice about Fugue SQL right now is that you can have an end-to-end workflow in DuckDB, and then you can translate it to Spark SQL, and a lot of the times it will run as is without code change. And that's sort of amazing. But that has to do with the fact that DuckDB's SQL interface matches Spark SQL's interface very well with like good parity. So now you have to find those edge cases where it doesn't map well, and then you have to make some kind of syntax for it so that we can eventually resolve it when you declare your backend without having to change the code that you already wrote. On the streaming side, we're definitely looking into adding Flink. Streaming will definitely take a different form, especially just because when you go from batch job to streaming, of course, latency has to go down. And the overhead with batch job is a lot more generous compared to having your overhead with streaming. So we definitely have to pare it down. It's certainly something we've been thinking about, how we can incorporate streaming frameworks as well. And that's something in the future plans.
The only thing worse than having bad data is not knowing that you have it. With Big Eye's data observability platform, if there is an issue with your data or data pipelines, you'll know right away and can get it fixed before the business is impacted. Big Eye lets data teams measure, improve, and communicate the quality of your data to company stakeholders. With complete API access, a user-friendly interface, and automated yet flexible alerting, you've got everything you need to establish and maintain trust in your data. Go to dataengineeringpodcast.com/bigeye today to sign up and start trusting your analyses. For people who are interested in getting started with Fugue, can you talk through the workflow of incorporating it into an existing project and how that might differ from the way that you would approach it if you're building something out greenfield?
This is a good question because a lot of times, like I think it varies depending where you are, how much code you've written in Spark scale, right? So let me first say what attracted me to start contributing to Fugue and getting involved with the project. So first of all, I worked in a payroll company as a data scientist. And payroll has a lot of these like custom business logic. Hey, if this person is this, use this. If not, use this other thing. And then there's a lot of nested logic in these if else's. But then what we had to do was we had certain projects that called for Spark because of the size of data. And we had other projects that called for Pandas. And then we had to re-implement the same logic twice. We had the Pandas implementation and the Spark implementation. And because we have these two sets of code that maybe live in different places that we have to maintain, it's very easy for them to fall out of sync. So what I wanted to do is I was very attracted to Fugue because I felt, hey, we can write our code just once, and then we can again specify, hey, run this on Pandas, run this on Spark. So at that level, like if you have something written already, like in Pandas, it's very easy to port it to Spark. But the challenge is if you have something written in Spark, it's a bit harder to bring it to Pandas because it's very coupled to the Spark framework. And that's exactly why Fugue wants to prevent locking into these frameworks. We want you to define your code like in the most native way possible and will be responsible. If you have a significant amount of code that is already locked in to Spark, it becomes very hard to use Fugue for new projects. But on the other hand, if you have a lot of Pandas code or Python code and you are going into that big data direction and you need to port it over, then it becomes very easy for Fugue to take over that responsibility of porting it over. If I were doing a greenfield deployment, I'd really look at that end-to-end workflow DAG type of setup because then it's very easy to prototype in Pandas. You just use your native Python or Pandas execution engine, and then when it's ready to put in production, you use Spark. It helps in local development because we talked about how much less code you have to test. We talked about you don't necessarily need a cluster to run your code, and then when you're ready, you can bring it to production. You reduce a lot of expensive mistakes as well because instead of testing your code on the Spark cluster and then finding out after an hour that it failed, like on a smaller sample with the Pandas engine, you can run your test, you find out something failed, you tweak it before you actually put it in production with the Spark cluster.
In terms of the capabilities of Fugue, at the surface level, it's very easy to see, okay, I've got this pandas logic, I'm just going to pass this through a transform function, and now I can run this on Dask or Spark. But what are some of the more nuanced or less visible capabilities of the Fugue project and Fugue framework that you think are worth calling out or that folks should take the time to investigate and understand more fully?
A lot of times we'll hear something along the lines of, I really need Spark's functionality because it does so and so, right? I'd like to point out that Fugue does not lock in like access to the underlying framework. So if you need a specific piece of Dask code or you need a specific piece of Spark code, Fugue is aware of the execution engine it's running on. So you can do some sort of if-else behavior on that execution engine and then use that Spark code and then use that Dask code. So if you already have a lot of Spark code written, then you can decide, I'm just going to write the Pandas equivalent of it. And then now I can do that if-else depending on my execution engine. And now I have this function that if I'm on Spark, it resolves to the native Spark code. And if I'm on Pandas, it resolves to the native Pandas code.
In your experience of working with Fugue, using it for your own purposes and interacting with the community, what are some of the most interesting or innovative or unexpected ways that you've seen it applied?
I'll talk about unexpected because this one took us by surprise. Like we did not foresee like this kind of use case. So we are talking to someone who they are in the Internet of Things space. So what they do is they have a lot of edge devices that have limited compute, but they want to be able to process the data the same way on their edge and on the cloud where they have more resources. So they're thinking, hey, I can use Fugue and then I can have that same code exist on both the edge device and on the cloud. On the cloud using a Spark backend or Dask backend, and on the edge using the Pandas backend. And now I don't have to rewrite anything. I just have one code base for my IoT stack, right? That's certainly interesting. The second thing is that I want to bring up a collaboration we had with PyCaret. PyCaret is a low-code data science framework that data scientists can use to for their end-to-end machine learning pipelines in very little lines of code. So PyCaret primarily runs on Pandas, but what we did for them was we can say, hey, if you add a Fugue backend to your code, then we can point like this piece of code to Spark, Dask, or Pandas, right? So now instead of just training, what they do is they have an auto ML with like 15 models, and they train all of these in parallel, right? Now we can say train them in parallel over Spark, or we train them in parallel over Dask by setting Fugue as the backend. So for a lot of open source projects, if they integrate Fugue into their stack, I think they can see that, hey, I have a Pandas based library now, but maybe if I use Fugue as a backend, I'll be able to apply it to the Spark engine as well, or to the Dask engine as well. So definitely we have a lot of open source collaborations that are in talk where we can port their library over to Spark or Dask for them without major rewrites on their end, because we solved it already on the abstraction layer level.
In your experience of working with Fugue, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
Yeah, so on a technical level, I would say the SQL parser was definitely challenging, because that's something like you're not definitely used to. And then like now we use Antler specifically, and like there's not a lot of resources on it. So now you have to figure out like how to build your vocabulary and then map those words over to the respective Python code. But on a non-technical level, I think this is very understandable now that I'm saying it, but we certainly have a lot of pushback because data professionals tend to be strongly opinionated. So, for example, we have a LinkedIn post that demos Fugue SQL. We get both sides of like, hey, this looks great. I can't wait to use Fugue SQL and that SQL interface on my Pandas data frame. And we get the other side where it's like people like not quite cursing us, but as close as you can get without cursing. Like, why would you ever want to use this if Pandas is very performant already, right? So also on the Panda side, what we see is that a lot of people kind of really love their tool, and really it takes quite a bit of convincing in order to expose them to like other things. Like for example, Pandas being the interface for distributed compute, sometimes people just want to stick with that. So I think this is pretty expected now that we are talking about it, but definitely it for us came as an initial surprise, and we thought, hey, people would see the value of Fugue immediately, but definitely we've learned to become better communicators about it over time as well.
In terms of people who are interested in being able to abstract their logic from the execution context, what are the cases where Fugue might be the wrong choice and maybe they're better served with a Modin or a Koalas or using one of these other implementations of the Pandas API for different execution contexts, or just writing their own abstraction layer to be able to translate arbitrary Python code into some other runtime?
With Modin specifically, I mean, I guess we don't have a Ray backend yet. If Modin has one and you need a Ray backend because you have a Ray cluster, definitely by all means go for it. Same thing with OmniSci, they have as a backend. But when that backend gets really developed anyway, at some point we would maybe add Modin as a backend or add Ray as a backend ourselves with Ray native code rather than go through Modin. So in that sense, I think it's just a matter of time before, like if something is really picking up, then we would just add it as an execution engine on our end. But to their credit though, if you switch your import and your program works perfectly, then maybe it doesn't make sense for you to rewrite it anymore and bring it to Fugue, right? If it does work perfectly. But I honestly find that a lot of times there is at least something that it's like, hey, this is not working as expected, right? And if that's the case, then maybe you should consider using Fugue where things are more explicit and things are more in your control rather than kind of sort of magical that, hey, this code is just ported and it wasn't necessarily one-to-one, right? Because a lot of times compromises have to be made. But there is one case where Fugue is definitely not the option for you, and that's for people or for teams. I've seen conference talks where people say something along the lines of, we had to edit the Spark code ourselves, or we had to create this like extension or change the memory buffer or whatever. Like these kinds of things where you have to edit the framework to fit your use case. you definitely are probably using Spark for some heavy duty use case that is maybe in the petabyte level of data. Like you're a big company, you have a lot of tech resources, you can do this thing. If it means that much to you to perform these optimizations, then Fugue is definitely not for you, right? Because we perform some optimizations, but only up to a certain level where it's like reasonable practitioners. But we would say most people are around this level anyway, of like your use case could probably be satisfied by Fugue unless you're with a really big company or with a really, really heavy duty data engineering pipeline. Otherwise, we think that Fugue can probably solve your use case, maybe with a bit of tuning or tweaking, but definitely.
As you continue to work on the project and evolve it and keep it up to speed with these different underlying execution engines, what are some of the things you have planned for the near to medium term, or any projects you're excited to dig into?
Yeah, so we definitely want to add on the application layer of Fugue because we have Fugue, we have this abstraction layer. What's nice about this abstraction layer is that we can now make a library and it's compatible with Pandas, Spark, and Dask. So we already have one in like Fugue Tune, for example, which is a hyperparameter tuning framework for machine learning. And now we can say, hey, run these model trainings on Spark or on Pandas as a backend, right? Now we want to explore other parts of the stack as well. So, for example, data validation. Can we make a data validation framework that is immediately compatible across Pandas, Spark, and Dask once you add a validation rule? Or, for example, for feature engineering, how can I use this DAG like to represent a lot of like transformations, and then how can I further optimize on that feature engineering DAG that's created so that it can perform better on the distributed engine such as Spark and Dask. So we're exploring Ray on our end as a backend. In a bit of time, maybe when some of the stuff matures a bit, it will certainly be able to be brought in and fit in as an execution engine. And then we're also, like we mentioned earlier, looking at that unified SQL interface, where how can we go further into the database and actually perform operations. Actually, on this front, what we did was we added IBIS as a backend already. So you can use Fugue IBIS to kind of use Python to query those database tables. But how do we do this on the SQL interface as well? Definitely.
Are there any other aspects of the work that you're doing on Fugue, either at the technical level or the use cases that it enables, or your work with the community, or areas of contribution that you're looking for help with that we didn't discuss yet that you'd like to cover before we close out the show?
We're definitely looking for collaborations with other open source projects. Like if you maybe have a project that works well on Pandas already, we can definitely bring that to Spark or Dask with you. So that's something we're looking into. And then if you also are a company that's maybe thinking of migrating to Spark or Dask for your pipelines, but don't quite know where to start, we're always happy to chat about that.
All right. Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
It's not that I see a gap, but it's more of I see a very interesting intersection because my day job, right, with Prefect is macro level workflow orchestration. So we deal with like full on data pipelines and like there's a very macro level DAG that tracks the state of these operations of these jobs and then reports some kind of state and then there's monitoring on that level. But then there's also the micro level orchestration. And I think this is kind of what Spark and Dask have and Ray has, right? Where they have a DAG themselves and their DAG also does retries on operations. Their DAG also does some sort of optimization, right? So we have macro level workflows and we have micro level workflows, which are more compute based. And what I've been thinking about myself is that the intersection of these tools is like pretty interesting in that a lot of the macro level guys are going in the micro direction and a lot of the micro level guys are going in the macro direction, right? So we have Ray that recently came up with Ray workflows, for example. And then Prefect, for example, has a very, very granular task definition. And I think the intersection of this is pretty interesting. And I haven't quite been able to figure out, like how this industry will turn out. But this is something I think we think about for Fugue as well, because, we are an abstraction layer for the micro level. Is there a way to unify that with the macro level as well, right? So no real answers, just some thoughts there.
All right. Well, thank you very much for taking the time today to join me and share the work that you've been doing on Fugue. It's definitely a very interesting project, and I'm excited to see more work being done to elevate the logical component of the work that we're trying to do so that it can be abstracted away from the specific execution context and implementation details of where the code is running. So appreciate all of the time that you and your collaborators are putting into that, and I hope you enjoy the rest of your day.
Yeah, thank you for having me. It's really an honor to be on this podcast just because of the previous companies and guests that you've had, and definitely been a fan.
Thank you. Listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.